let's say, move that aside. All right, it says 300 milliliters of a 0.2 molar potassium acetate solution is mixed with 200 milliliters of 4 molar, whatever that got. Acetic acid solution. All right, so here's the deal. You have 2 beakers. You're mixing the things in those 2 beakers together, so they're in 1 beaker. Yes? Yes? Anything come to mind? Thank you. Total volume has to come to mind. All right. So here's the deal. I've got a beaker, when I mark pen, a beaker and another beaker to make a big beaker that is 500 milliliters, agreed? Okay. In this first beaker, I have 0.3 liters, and I have a 2 molar solution of conjugate base. So I have 0.6 moles of conjugate base. Why am I not writing in potassium? Because we don't care about him. That's right, because he's just neutral anyway. And in the other beaker, I have 4 molar, Snagit, 0.2 liters of a 4 molar weak acid. So I'm going to get 0.8 moles in this first beaker of my weak acid, HC2H3O2. And so when I put them over here, that doesn't change. Those mole values are the same. What does change is the volume and thus their molarities, but their mole values are unchanged. All right, so that phone gets turned upside down, please. Thank you. And so I look at that, and that's where we say, what do I have? I have a buffer, because I have a conjugate base with his weak acid. Agreed? Yes. Okay. And then I have to say, how do I ever solve for the H plus of a buffer, or the pH? And what do we call that? We call that the HH. So I must get in the habit of saying to myself, if I have a buffer, I'm going to use the HH. What in the world, Ms. Matney, is the HH? Glad you asked. It is nothing more but the Ka expression, which looks like this, rearranged. Is that the Ka expression for any weak acid dissociating in water? It is. And if I take that fellow and I rearrange him, I end up getting Ka times weak acid over conjugate base will equal my H plus. That is called the HH. You with me? Okay? That is the HH. And we're always going to use that when we have a buffer. It's nice and simple and easy because it means I only really have to have the moles, and I'll show you why. See, Ka, which is 1.8 times 10 to the minus 5, times the acid over the base is 0.8 moles over 0.5 liters over the base, 0.6 moles over 0.5 liters. And that multiplied together equals my H plus, which you can't see over in that purple part, and I can't figure out how to get it away, so we'll just leave it right now. Now, there you go. What I really have then is 1.8 times 10 to the minus 5 times 8 over 6 equals H plus. Agreed? And so we got an H plus, and we took the minus log of it, and we got a pH of 4.620 for my buffer. 4.620. Okay, did we get that? That was my goal. Was everybody got that on A? Okay, did some of you use molarity instead of moles? That's why. That's okay. It's okay. It's just that you probably did some rounding. I just want to, I put mine right there. These all values? I just put 1.8 times 10 to the minus 5 times 4 over 2.
Imagine they make this one.
4 over 3. 4 over 3. So you have to divide No, what I did in the beginning was volume times molarity gave me moles, and then if I divided by 0.5, I'm cutting the 0.6 in half and the 0.8 in half. You got to divide them by total volume. But if you use molarity, 0.6 divided by 0.5 is what is it, 1.2? 1.2, and if you say that divided by that is 1.6. So, all right, let's just stop a moment. It should not be that far off. Clear, clear, clear. All right, 1.8 times 10 to the minus 5 times 1.6 divided by 1.2 is 2.4 times 10 to the minus 5. Okay, if I minus log that, you should get 4.6197, which turns into 4.
1.8 times quantity 4 over 2 equals 3.6 times 8.
That's not the right quantity, because this ends up being 1.6 and this ends up being 1.2. So it's 4/3. Okay, all right, let's go back. I want all eyes on me, okay? You cannot use their molarities when they're in two separate beakers. You cannot use their molarities when they're in two separate beakers. You cannot use their molarities when they're in two separate beakers because they're not a buffer in two separate beakers. This is a weak acid dissociating all by himself. Ka equals x squared over molarity. And this is a weak base floating around all by himself. Kb equals x squared over molarity. When you pour them into one beaker, they are no longer the same molarities, are they? Same moles to new, bigger volume called total volume. Okay, this is what happens. Let's do a little quick aside for a moment. Wherever my pen is. I need some space. And I'll come back. Okay, so originally you had 0.3 liters times 2 molar, yes? And you got 0.6 moles of conjugate base, agreed? When you divide that point by 0.5 liters, which is your total volume, you're going to get out 1.2 molar conjugate base. That's the molarity of the conjugate base when he's in the buffer. Before he was 2 molar, now he's less molarity because he's in a bigger volume. Same moles in a bigger volume. And then you take, the other one was 0.2 liters in a 4 molar, and you got 0.8 moles of weak acid, and when you put that over total volume of 0.5 liters, you end up getting 1.6 molar for your weak acid. And so now 1.8 times 10 to the minus 5 times 1.6 over 1.2 is how you get your H plus, right? So you can't use their molarities when they're in two separate beakers because they're not a buffer. You can't use HH. If they're not a buffer, you can't use HH. Okay? Now, if we go back to my setup, you'll see that technically, yes, you can use molarities, or you could have just said moles over moles, and you would have gotten exactly the same answer. Why? Because they're in the same total volume now. So moles divided by total volume divided by moles divided by total volume, that total volume value goes away. And that's what I was trying to show y'all right here. You see how my total volume goes away? So you can do it either way. Jordan, Austin, if y'all like to use molarity, you can use molarity all day long. If you would rather use moles, you can use moles. Yes?
Pretty much the same thing as all you've already been doing, which is taking the
You're plugging into the HH for a buffer? Yeah.
Okay, yeah.
Yeah. You haven't missed anything yet except time to try to get the problem done. And some frustration on some students' parts. Oh, what did you say? What did you say? It was on the owl. A little practice always kind of helps before class. Oh, thank you, Hayden. Yeah. Yeah. Okay. All right. Next frame. Next frame. New frames, Ms. Matney. All right. What happened? What happened? What happened? You got me all excited, Hayden. Oh, I was on the wrong frame. Goodness gracious. Y'all didn't think. Okay, whatever. All right, so frame 2. We were on the frame that had D on it. All right, here we go. This is the same problem, but now it says, how is the pH going to change? How is the pH going to change if I end up adding some H+? It's going to change, is it not? Yes, it is. All right, so here we go. Let's draw our little beaker. Our beaker is 500 milliliters or 0.5 liters. I have 0.6 moles. I have 0.8 moles. And to it, I'm adding in some H+. Let's look at how much H+. I'm adding in that much, kick him to the curb, H+, yes? So I'm adding in 0.2. When I say 0.1 liters times 2 molar, that gives me 0.2 moles of H+ added in, yes? All right, let's look at what that looks like. H+, who is going to gobble up my H+? The conjugate base. Acids and bases react together, not acids and acids. All right, so I get HC2H3O2. Let's put in what we have. 0.2, 0.6, 0.8 originally. But because this is a strong acid, I have what kind of arrow here? A one arrow reaction. That means the reaction keeps going until the limiting reactant is used up. Who's my limiting reactant? H+, because he's a smaller value. 0.2 is subtracted from that side. 0.2 is added to that side. You get 0, you get 0.4, you get 1.0 moles. Okay, question. What do I have? You're supposed to stop, look and listen, and say, what do I have? I got a buffer. What comes to mind? HH. So I'm just going to go plug in to the HH, which says 1.8 times 10 to the minus 5 times 1.0 over 0.4 equals my H+. And then I'll minus log it, yes? I added H+. The pH should go down to about a 4.3-ish. Right? Yeah, it goes from about 4.6-ish to 4.3-ish. Because you took a buffer and added a little bit of H+ to it, yes? Okay, so the next scenario is, what if you add OH- to that same original buffer? So you have your beaker, you have your 500 milliliters, 0.5 liters, 0.6 moles of conjugate base, 0.8 moles of weak acid. Now you're adding in 0.6 moles of OH-, and the Li gets kicked to the curb, yes? Okay, so OH-, now who's going to gobble up OH-? The acid. Acids react with bases, not the other way around. Bases don't react with bases, acids don't react with acids. So I get a single arrow because this guy is a strong base, single arrow, and I'm left with C2H3O2 and HOH. Don't worry about the HOH. All right, 0.6, 0.8, 0.6. Matt, you with me? Okay. And I've got to now subtract the limiting reactant. Who is he? The OH value. So minus 0.6, minus 0.6, plus 0.6. And it's just like doing X's, except now I have a real value because I have a single arrow, and that's because I added in strong. Strong causes single arrows to happen. Okay? I'm left with 1.2, 0.2, and 0. Stop, look, and listen. What do I have? I still have a buffer. How do I solve for the pH of a buffer? HH. So Ka times 1.2 over 0.2 equals H plus. Yes? All right, let me stop before we go any further. Have I done anything on B and C that doesn't make sense? Sure?
So yeah, you add in after H reaction, you just add the part pH plus or pH minus to the reactant side equation.
Okay. And if you add in base, you put in the weak acid with it. And if you add in acid, you put the conjugate base with it on the reactant side. Reactant side. No, what I'm saying is like here, see how this is OH plus weak acid? The one before it, B, was H plus conjugate base.
Oh.
You have to have, if you add in base, you got to put the acid right here from the buffer.
Yeah.
If you add in H plus, you got to put the base here from the buffer.
Okay.
And then figure out what it makes on the other side, which will be the other fellow plus maybe something else. In this case, it was conjugate base. Back in B, you made the weak acid. It does. It does. Yes. I just didn't add that part in. The Ka is the same Ka back from the top, 1.8 times 10 to the minus 5. That part's not changing. It's just this ratio that's changing.
Oh, okay. And then you just solved it from there and then
Negative log my H plus. Yep. Yep. Okay? All right. So how in the world, because now I got to erase everything we had up here before. How in the world is D different? It's not, but it is. It's not, but it is. So in D, you still have the same scenario, 0.6, 0.8. You're adding in 0.8 moles of OH minus from a strong base because you're adding that in. Kick Na to the curb, you have OH minus. Okay, so same scenario like up in C, you're going to say OH minus plus the acid is not, yields C2H3O2 minus and some water. Water. Okay. Now, you have 0.6, 0.8, and you're putting in this time 0.8. I want everybody to look up here. 0.8, 0.8, 0.6. Who's my limiting reactant? Both. Oh, I love it. Both. There's no excess here. That means there's a complete reaction. Nobody's left over. You know what we call that in an acid-base titration? Equivalence point. Why do we call it equivalence point? Because they're equal. It means complete reaction. It means in chemistry, perfection. That's what it means. Perfection. They're equal. Perfection. Anything but. Trust me. I'll let you ask my husband, my children. Anything but. 0, 1.4. Okay. Again, what does Ms. Matney want you to do? I want you to stop, look, and listen. I want you to say, what do I have? Not a buffer. Can't use HH if I don't have a buffer. Matt says, so do you do rice? Because here's what you got to think about. I have a weak base floating around in water. Is that all I have over there? A weak base floating around in water. If you were back in chapter 14, what would you do with a weak base floating around in water? You'd rice it. You'd do what you did. You'd write the dissociation equation. You'd do minus x plus x plus x, right? You would. So you're back in chapter 14 now. You're back in chapter 14. Some are you working on now? Making sure. You have a weak base floating around in water. That's what this looks like. C2H3O2 minus sitting in water. How much of him? 1.4 moles? Total volume. Making in equilibrium, HC2H3O2 plus, and that's not a minus, plus OH minus. The minus is right there.
So if there's no excess, what you add in actually consumes the buffer?
It does. In fact, we say it destroys the buffer. It destroyed it. Okay, what do I have? If you go back to what you just wrote down, you had 1.4, but on the other side you had 0, 0, yes? So that's what you have. So you're way back now at the beginning of chapter 14. You just got dissociation. How do you solve for the OH minus value here? Because you're going to go minus x plus x plus x. How do you solve? You got to get the KB and say KB equals x squared over molarity. Yes? All right. How did you get total volume, Abby? How'd you get it? Because you got it. How'd you get it? All right. The two beginning values from my two beakers were 0.3 and 0.2 liters, made 0.5. And I added in on letter D, 400. Letter B, I added 400. That makes 900 milliliters or 0.9. Now, if you put that in right here, you get 1.55 molar. 1.955 molar. Yes? And then the rest of it is just saying, I know how to do this because this is old stuff, Ms. Matney. I can handle this. I can handle this. I just don't have the KB yet. But what were you given? The Ka. So you can say Kw divided by Ka equals x squared over molarity. Yes? And when you get x, it's going to be OH minus. Yeah? Because it's a Kb. Because it's a base. Do you have to show me all this all over again, or can you just jump right to here? You can do what you want. That's right. At this point, you can do what you want. Because you don't have to show me the ice chart all over again, but you can. If it makes more sense, you can. Yes? Okay. Now, I need to stop this a moment and then tell you something.